So after determining the minimum number of registers required to implement this program, this is 3. So the data need to be allocated to these registers now, and this is done by forward backward register allocation technique. So this can be performed using an allocation table. So this is the table for this corresponding data. So 3 registers are required: register R1, R2, R3, and the variable A, B, and C will be appropriately assigned to these registers. So step 1 is to input each variable at the time step corresponding to the beginning of its lifetime. If multiple variables are input in a given cycle, these are allocated to multiple registers such that the variable with the longest lifetime is allocated to the initial register and the other variable are allocated to consecutive registers in decreasing order of lifetime. So starting with variable A is produced at 0th interval. So the first column is representing number of cycles. Okay, so starting from 0 to 7. So cycles starting from 0 to 7, and A is produced at 0th interval. So we have to input A at 0th interval, and B is produced at first interval. So B is produced at interval 1, that is cycle 1, and C is produced at 4th cycle. So C is produced at 4th cycle. After that, each variable is allocated in a forward manner until it is dead or it reaches the last registers. So this means that if register I holds the variable V in the current cycle, then register I plus 1 will hold the same variable in next cycle. Okay, so the now question is why we have not assigned registers to variable A, B and C when it is produced. Okay, the simple answer is that let's say that A is produced by computational unit A, B is produced by B, and C is produced by computational unit C. A can be adder, multiplier, anything. So A is produced at 0th cycle, B is produced at first, and C is produced at 4th cycle. So for A, it is being produced at 0th cycle. So this is available at the output of A. Okay, in the current cycle, output A is generating A0. So A0 don't need register in this particular cycle. It is already available at output of A. Okay, so in 0th cycle, A0 will be available at the output of computational unit A. In the next cycle, that is first cycle, this A will start processing, this A will process new sample and produce new output, let's say A1. Okay, and now we have to save this A0 in some registers. So in the next cycle we have to assign some register to this A0. Same applies for B and C. So during the time of its production, the variable doesn't need a storage element, and in the subsequent cycles we have to then properly store the variables till it is dead. So now we will allocate the registers to this variables sequentially. Okay, so starting from cycle 0, A is produced. Okay, during next cycle B will be produced and A will be transferred to register R1. So this input means that we are looking the system as whole. Okay, so this variable a is produced during cycle 0. This is what it means writing a in the input column. Okay, so in the next cycle b will produce means it is now generated in the system. Okay, so in the next cycle now b needs to be stored in some register. Okay, so b will be shifted to r1, and for this a need to be shifted to r2. So b is shifted to r1 and a is shifted to r2. So this is the sequence. First the computational unit will produce the variable, then it will shift to register r1 in the next cycle, and then r2 in the next cycle, and then r3. So this is the sequence: ri plus 1, ri plus 2, like this. Okay, so in the next cycle this will be shifted to r3, b is shifted to r2. So now a is in last registers in third cycle, and a is dead at the end of fourth cycle. So for one more cycle we have to save this variable a. So now it will be allocated in backward manner, and in the fourth cycle b will be moved to the register r3. Okay, so this means that r2 will be vacant. So during fourth cycle b will move to register r3 and r2 is available, so a can be moved back to r2, and at the end of the fourth cycle a will be consumed, so we can write that a is dead, and we can write a to the corresponding output column. Output column means now it is consumed, there is no further use of variable a. This is the sense of word output in this table. Okay, so during fourth cycle c is produced, and a is moved backward to, that is from register r3 to r2, and b is shifted to register r3, and also a will be consumed. It means that by the end of the fourth cycle a will be dead. Okay, so the dead or consumed variable will be written in this column, output column. So in fifth cycle c will move forward, and now b is at last register, and the life cycle of b is till seventh cycle, and now it has to be allocated register in backward manner. So b is now transferred to register r2. Okay, so at this point only one register, that is r2, was available for backward allocation. If multiple registers are available for backward allocation, first try to choose a register such that backward allocation has already been performed from the last register to this register. So we have already performed backward allocation from r3 to r2. Okay, so for next backward allocation we have to perform the allocation in same way, that is from r3 to r2. Okay, if r1 would have been available, we could have transferred b to r1 or r2, but in this case we have chosen that a will be moved to r2. It can be also moved to r1, okay, but we have put a in r2. For next backward allocation we have to choose the same register, and in this case A could have been transferred to R2 or R1. Okay, the distance between R3 and R2 is small as compared to R3 and R1. So in this case we have chosen R2. So now we have to keep one more important thing in mind, that this DSP program is periodic nature of this DSP program. Okay, so the time period is n. So in this case the value of n was 6. So this is first iteration, and this cycle 6 and 7 belongs to second iteration. So 0 2 5 6 cycles in any iteration. Okay, because of this periodic nature, if Rj is occupied with a variable in cycle L, then Rj would occupy the corresponding variable in cycle L plus n also. Okay, so we have to keep this thing in mind, and we cannot allocate this register neither in forward or backward manner if this is the case. So during any nth iteration, so I have already mentioned that during any nth iteration, A will be generated at cycle 6L plus 0, B will be generated at 6L plus 1, and C will be generated at 6L plus 4. Okay, so here you can see that A is generated in the 0th cycle in this particular iteration, and in next iteration it will be again generated by the same computational element, but we don't have to show this explicitly in the table. We will only show for the first iteration. So during the first cycle of subsequent iteration, A is at input. Okay, so no registers is required during the first cycle, so there is no problem in this. Now at first cycle, A is in register R1. Okay, so in the next iteration, the 7th cycle, next generated value of A will be also in R1. Okay, so during this cycle we cannot allot R1 to any other variable, so we will shade this portion that it cannot be allocated during the 7th cycle, because A0 is generated in first iteration, A1 will be generated in second iteration, and due to periodicity A1 would have been in this place. Okay, so we are not writing A0, A1, AN explicitly, we are just writing for A, B and C. We have already included the periodic nature of the DSP system. Okay, the same thing we have to check for variable B. So B is generated in the first cycle, it is at input, and in second cycle it is in register R1, but we have drawn till only 7th cycle. Okay, so no need to worry about that. And C is generated at 4th cycle, and it will be generated next in 10th cycle, so we don't have to worry about C also. Okay, so we have to just take care of the cycles that we are including in the table, and we have to worry about the variable that will be again generated in this duration. So A will be generated again in 6th cycle. In the 7th cycle it will be transferred to register R1, same as this case, so we will not allocate register R1 to any other variable. Okay, and now completing this table, so in the 6th cycle B will be again moved to register R3 because C need to be moved to register R2, and during 7th cycle B will be moved to register R2 in backward direction. because C need to be moved to R3, and at the end of the 7th cycle B and C both will be consumed. So B is consumed, C is consumed, and B is also consumed. So at output we will write B comma C. So by using this register allocation table and folding equation, we can draw folded architecture. Okay, so for this example we don't have folding equation, so we cannot draw architecture. This example was taken to explain the concept of lifetime analysis and register allocation. So now using the technique we will reduce the number of registers in this folded architecture. Okay, so it is having 6 number of registers and we have folding equations for this. So we have to calculate the lifetimes of the variables involved in this system, and then we will calculate the number of registers, minimum number of registers that is required to implement this given system. And with the help of register allocation table and this folding equations, we will draw the folded architecture with minimum number of registers.